Right, welcome on board everyone. We're going to move it on to the next topic here. This is P12. Okay, so the first start of P12 is magnetic fields. And we look at P12 and P13, which is electromagnetic induction. Don't panic, I'm throwing lots of words at you. But they're in two halves. Okay, we look at one side, magnetic, and what it does is it sets us up for P13. If you can get one side right, the other side is like a mirror image of it. One thing happens one way, and if you flip it around, it happens the other way. So if you get P12 right, P13 is a doddle. Okay, so we're going to start off with the basics. Some of this you'll already have seen through Key Stage 3, even probably back at primary school. Fun with magnets. So for those of you at home, I've got a simple bar magnet here. I'm going to use it for some demos during today, and I will try my best to describe to you what is going on. Currently the magnet is spinning around the table. Okay, so moving on. I've got a blank screen's come up, don't panic, it's meant to be blank. So one of the things you need to do when you start P12 and P13, and I'm going to try and draw this on the board, and we're going to treat this like a piece of A3 paper. So you don't probably need to do this in the classroom, but at home, just for some context, what I would suggest is split your revision material into two halves. And put P12 on one side and leave P13 until we get to P13. So on this side we're going to do magnetism, and on this side we're going to do electromagnetism. Now if you get this started straight away and you leave half, you'll find this really easy to set up. It'll mean a lot less work long term for you, and you've got two things that mirror image across both sides of the page. That makes sense? Does anyone not understand what I mean by that? But get started earlier. Okay, so that's where I suggest with revision material. Okay, so with magnetic fields, the very first thing I would start off is give me some examples of forces. Okay, contact and non-contact forces. What have we got in the classroom? Give me an example, either side. You're going first, so any force will be on this table. Give me an example. Go on. Friction. Okay. Contact or non-contact?
Contact.
Yeah, absolutely. I'm looking at the board while I'm writing. That's very dangerous. Give me another one. Shout them out. What else? Gravity. Now, is gravity a force? Well, actually, technically it is, but we don't treat it in GCSEs as a force. We have acceleration due to gravity, but acceleration's not a force, it's an acceleration. But what does gravity give us? Why don't we float off into the sky? What would I measure if I put you on a set of scales? That's mass. Don't measure mass.
Oh, newtons?
Yeah, newtons, or in layman's terms, your weight.
Ah.
Yeah, which is in newtons, you're quite right. Which side would I put that on though? So if I was going to put gravity on there, which we will just because we talked about it, contact or non-contact?
Non-contact.
Absolutely. If you could touch gravity, you'd be very, very important in the world. Another one? They're all poised in the classroom. It's Monday morning. Hello? Come on, there's got to be some more forces than that. Go on. Air resistance. Yep, contact, non-contact.
Contact.
Oh, I forget the pen hovers on the board, which kind of gives away where I'm going, doesn't it? Air resistance, absolutely. Why is it, a lot of people go, well, you can't see air resistance, so how do you know it's contact? You stick your head, now don't do this at home or otherwise, stick your hand out a car window, what happens to your hand? You shouldn't, but, so the comment from the classroom is, I love doing that, but you shouldn't for a couple of reasons, one being telegraph poles don't tend to take too kindly to your hand, or vice versa. But what's pushing against your hand? Specifically?
Wind.
Not wind. What you feel is wind. That's a relative term to us. But what is actually hitting your hand? That's what we call the whole system. You're not wrong. But what's hitting your hand? Anyone?
A force.
It is a force, but a force from what? What's actually, if we could have a giant microscope right next to our hand, what would we seeing hitting our hand one by one?
Particles.
Particles of what?
Air.
Air, absolutely. And there's just enough of them that it creates enough of a force. If you had one particle of air hit your hand right now, and I guarantee it's occurring, put your hand up in the air right now. Right now there are air particles hitting your hand. Can you feel them?
No.
I hope the answer is no, otherwise it ruins it. Okay, you can put your hands down now. The reason you can feel when you put your hand out a car window is because there are so many of them. Does air have mass?
No.
Yeah.
Okay. You went, Amelia, you went quite definitively yes. Do you want to tell us why you went yes? It's a 50-50. So my body language gave it away. Okay. Does anyone think yes for a reason? All right, you went no. Why'd you go no? I'm going to suggest you are wrong, but why do you think no? Because that might help us find the yes.
You can't really like weigh air.
Mm-hmm. Okay. Let me ask you a different question then. Where is most of the air on Earth? Is it down by the surface of the ground, or is it up higher in the air?
Up in the air.
Okay. Can you breathe as you go higher and higher?
No.
No.
So what must there be lack of when you go up?
Air.
So where is most of the air? Close to the ground. So if it's being pulled to the ground, why would it, if it had no mass, why would it do that? Gravity wouldn't affect it. So it must have mass. Okay, so actually a cubic meter, so if I've got a meter ruler and had 3 of them, so meter by meter by meter, for those of you at home, I'm trying to draw, no idea what that is, sounds well. So if I took a cubic meter box of air, how many cubic meter boxes do you reckon would fit in this room, roughly? Go on, give me a rough number, what do you reckon?
How big is the box?
How many 1 meter by 1 meter by 1 meter boxes would fit in here? What do you reckon, guys? Come on. 100? I've got 100. Anyone?
No, I would say about 200.
About 200? Yeah, I'd say they're not unreasonable numbers. I was going to go around 75 to 100. Okay. What if I told you each one of those boxes actually has, and it does vary a little bit, 1.2 kilograms of air in it. So there is a mass of air in this room. Okay, that's what you're feeling when you stick your hand out the window. You're pushing your hand through all those air particles, and they all add up. There's obviously billions and billions of them, and they're all, and the ones hitting your hands are all contributing a force. That's what we feel. Okay, right, we got stuck on air resistance for ages. Give us some other ones. What else we got? What's the one when I'm pulling on a rope, or try not to give this away. So if Amelia and I are having a tug of war and we've got a rope between us and I'm pulling, Amelia's pulling, and no one's moving, but we're both pulling on the rope, so there's a force involved.
Tension.
Tension. Okay, so let's put tension in. Contact or non-contact? What made you say contact? Because we had to physically apply it. Yep, good, I like that. It's reasonable arguments. Let's put tension over here. Right, what else we got?
Swollen, like twisting.
Yeah, okay, so we could just put that under push and pull, or what the proper name is the normal force. Okay, so if something's twisting, it's having a force applied to it, and the twist is a reaction of tension, effectively. We could put a lot of things under the band of tension, but to get something to twist, you're quite right, you need to apply force to it. Right, so we've dealt with a lot of contact forces. What about the ones you can't see? We talked about gravity. What else? They've all gone very silent in the room. Give you a hint. Is this? I'm holding a magnet up. Is this applying a force to anything?
Yeah.
Is it trapped?
Did it apply a force to the staple?
Yeah.
So it must be a force. And what do we call it? What's this force? Magnetic force, yeah, absolutely. Let's put magnetic in there, guys. It is the topic of today's lesson. It's up on the board. It doesn't say magnetic force, to be fair, but magnetic fields create magnetic forces. And the last one we're going to put up there is something to do with, I won't give you too much of a hint here. It's to do with electricity. We talked, it was one of the lessons we did just before we stopped doing lessons and moved to revision. If anyone was paying attention at home. I'll give you a hint, it starts with
Electromagnetic.
Close. Starts with air. Static. Yep. Okay. Electrostatic. Okay, and that's when you're dealing with individual electrons and individual charge. Okay, so I don't think we've missed any. Have we missed any? Oh, of course we did. So drag is air resistance, electrostatic, friction, we got magnetic, gravitational, fine, we did talk about gravity. The last one on the bottom there, guys, upthrust. What is upthrust?
Is it something like so an aeroplane?
If you say thrusting up, I'm going to laugh at you. You know that, right?
No, I'm not going to say that.
No, it's all right. Classic misconception. It's nothing to do with aeroplanes. I promise. I promise. It's more to do with another type of vehicle that's not a car.
Boats.
It's to do with boats. So where would we find upthrust on a boat? It does have to do with floating. What's pushing on the boat?
Sea.
Yes, or you simplify that. The wet stuff that you have in your hand. Water.
Oh.
Yeah, okay, so it doesn't have to be the sea necessarily. Water is pushing up, so what's the boat doing? What's the boat trying to do? The boat's got weight, right? It's trying to force down. But something is stopping it continually going down. It's the force acting back in the opposite direction, and we call that upthrust. Contact or non-contact?
Contact.
Absolutely. Okay, and it's all got to do with buoyancy. If I made the boat the same density as the water, which would be quite tricky to do, but let's assume I could do that, what would the boat do? Sink, yeah. Well, it'd have to be slightly more dense than the water, but yes, effectively, the way we make a boat less dense is we don't fill it up with water. Okay? If you slowly fill a boat up with water, it'll get heavier and heavier and heavier until eventually the density of the boat is greater than the density of the water, and it will sink. Okay? Right, so that's a good intro to all the forces involved. Let's move on to the next slide. That we need to get out of this lesson. We have to look at the force rule. Okay, it's a lot simpler than it sounds. We literally have a look at what two magnets will do when they're near each other. Simple as that. Most of you will intuitively already know the answers here. What we're really looking for is using the right keywords. Okay, that's what this is all about, showing you understand by not making, you don't want to use the words that kids in primary school would use. Okay, we need to use the proper words. Okay, we'll get to that in a second. We're going to look at the pattern of a magnetic field. Okay, this is one of the demos or perhaps practicals we might do in class. I typically do it as a demo. I find it's really almost too easy. I can show you, or I can just draw it for you, which might be easier for you and the people at home, and we'll talk our way through it. And we'll have a look at induced magnetism, which is why I've got a whole bunch of staples here and a magnet, and I'm going to demonstrate it in class to the people here, and I'll try and talk my way through it to you at home. And we're going to have a look at what a permanent magnet is versus an induced magnet. Okay, that's what we need to take away from today's lesson. It's building blocks for other things later on. Everyone happy with that? Okay, let's move on. Okay, here's the force rule. Now there's lots and lots of info there. What we really are interested in is the three key things that generate force in a magnetic field. And it's the distance. The first one is, and you could just say the force rule. So write down the force rule. And I would then put like a little subheading, things that affect magnetic force. Little semicolon in there, and I would have each of these as a bullet point. The distance from the magnet. That you should probably be able to figure out in your anyway. If you're 1.5 meters away from a magnet and you're a piece of steel, not a lot's going to happen. As you get closer and closer, you'll see that it starts to pull towards the metal, and when you're really close, it jumps onto the metal. Okay, that's not anything you haven't experienced before if you've ever played with a magnet. All right, I'm just trying to put it into context for you. That's point number one. Point number two, we need to know the direction of the magnetic field is from the north to the south. When we draw this later, that's really, really important. But if you don't have that as a force rule, you won't be able to use it as a key point when you're making an argument. So everyone writing these key points down? Everyone writing them down? Not the whole lot, just put down the bits in red. Put it this way, if I've gone to the trouble of making them red, they must be important. And I don't want people writing down huge amounts of information. I'm just looking for key points. So I would put this under the force rule, and the things that affect the magnetic force, here are our 3 bullet points. Distance from the magnet, the magnetic field line is from the north to the south, and the last one, needle points in the direction of the Earth's magnetic field. Okay, so the needle we're talking about the needle in a bar magnet or compass. So a compass in its own right is just a little floating magnet, nothing else to it. Anyone done Duke of Edinburgh yet? Did you carry around a compass? Did you use it? Did you get lost? Those who shook their heads for not using compass, funny enough, got lost. Compasses are really, really good as long as you understand what the shortfalls of them are. Okay, but you should 99% of the time be relying on them. Because guarantee you, the one person who relies on GPS and it runs out of battery will be the one person looking at very blankly at a map going, how do I use this thing? Okay, so we're just taking down these notes here. So there's 3 main points for the force rule, and then we'll move on from there. And I was no different, I got lost too. Then I know how to use the compass. All good there, nearly got them all. Don't need to write down the whole lot, remember, just the key points in red. Okay for me to move on? Alright. Okay, so here are 3 example questions. The one on the left is taken from a GCSE paper, a foundation paper, so fairly basic one. But you can see you need to do a lot to get the 1 mark. Okay, so you need to put 5 words in the right place. Can we have a go at the one on the left, please, guys? Just to get us started, I want to see where we're at, what we know keywords, because there's some keywords that we haven't talked through yet. And that whole terminology of like poles, unlike poles. So that's new to you. Let's see what you can do. So have a crack at that, and then we'll talk about the one in the middle, and then I'll worry about the one on the far right hand side later. So yeah, so could we, well, how about we just do like poles, we'll do it together. That makes sense? Like poles will attract. Okay, hang on, I'll see if I can draw. I think I can draw on this. Yep. Will they attract? So if I get 2 compasses, 2 magnets even, I put north there.
Will they not repel?
Okay, can you convince everyone why?
Because if you have north and north, they face each other.
Yep.
They don't.
What if I have south and south?
It's the same.
Same problem?
Yeah.
Okay, so they actually repel. Okay. So like poles will repel. Good explanation, Will, thank you. Unlike poles, so if we've got a north and a south, or a south and a north, will attract. Okay, well, here you go. If you get one, getting the other is pretty straightforward. Lines of magnetic force come out of the which pole and go into the which pole? We just had that on the previous slide. They will come out from the north, which means they go into the
South.
yeah. Okay. Lines of magnetic fields can be plotted using a compass. Now I'll talk in a little bit more detail what that means. Okay, when we get to the next slide, we're actually going to have a look at bar magnet in a bit more detail. These ones over here, guys, this question here for 3 and 4 marks 2 magnets are brought together, explain what will happen. Okay, so this magnet here, we'll call this magnet A, and this magnet B. You don't need to draw this, I'm just looking for your interaction here. So magnet A is suspended on a piece of string in a little, I don't know, call it harness, and it's just floating around, spinning. And it will just spin around a little bit, it'll settle down after a while. And then I bring magnet B to it. Now, to start with, if, let's just say we've got a north here and a north here, what's 2 like poles are going to? Repel. So what's this magnet going to do? This A? Spin. Okay, it's going to repel. It's going to spin around this way until this south is now going to be approaching this north. What are they going to do? Attract. So what are they actually going to end up doing? they're actually going to stick together, aren't they? They're going to come together. They're going to, magnetic fields are going to bring them and draw them together. They're going to be held by magnetic force. It is a force. How do we know it's a force? What are you going to do to get those magnets apart? Pull. So you're applying a force to overcome the magnetic force. Okay, that's how we know it's a force. So that's a really, really simple experiment that really confused a lot of people. They really didn't know what they were looking at. Maybe a bit of stress thrown in the mix there as well. Under GCSE conditions, you'll be surprised what people will start to ramble on about and make up nonsense. Okay, so this is about being able to use the right words. So common things were the norths will push each other away. No marks for that. They will repel, was for the mark. Okay, the south and the north will attract. We had things like they will stick together. No explanation of why. Okay, so you need to use the right words in the right context. That's why we go over this. It might sound like we're going back into primary school a little bit, but it's just to make sure we get the keywords in the right place. Every 10,000 years, I'll do the one on the far right hand side. Every 10,000 years or so, the Earth's magnetic field changes direction. It does what? Changes direction. North becomes south and south becomes north. Imagine if you were walking along with a compass and it happened while you were on a D.V. weekend. And it does happen very rapidly. Over a matter of seconds, it flicks over. How would you know? I mean, imagine you'd all get very lost first, but then how would you figure out what had happened? Yeah, everything would be completely back to front. You think you're walking towards something, you'd be walking away from it, and vice versa. So the penny would drop, but I imagine we'd probably end the D.V. weekend there and then. I think that would be the sensible approach. I'll get into that in a bit more detail later on. Okay, this is the most important thing. You draw a bar magnet for me, please, guys. Do this at home, straight on your revision material. I'm going to walk you through. This was for 3 marks in a GCSE paper. How do you get 3 marks out of this? Well, I'll show you. The first things first, you had to label north and south. So they're already done on the magnet for you, north and south. But if you are given a blank, I'll draw one over here. So if you're just given a blank rectangle, you'd be expected just to label one side north and one side south. It doesn't matter which one. Okay, it doesn't have to be always on the left. What comes next is more important. We talked about magnetic field goes from where to where. Go on, Alex. Paying attention?
North to south.
North to south. Good. Well, let's draw one in. Let's start here. Goes from north around here to, see if I've still got my artistic ability. There we go. North to south. How would we know that's going from north to south? How would I've drawn a line. How would I know it's going from north to south? How could I denote that's what it's doing? Well, that could be going from south to north. What do I need to add to this? So I know. An arrow. Yeah. So arrow, let's add the arrow in. North to south. Okay. Now, at this point, believe it or not, we've got 2 out of 3 marks. But that's not everything you need. You need to have at least 2 field lines, because there are many. Didn't quite get that right. Arrow there. And they come out of both sides. They're not always equal. In fact, they very rarely are. So that's my excuse for my bad drawing. And of course, common mistake here, people draw the arrow going to the right at the top and then go, for some reason, go the other way. No, it's always north to south. And in fact, we're going to make this even better. Let's draw these ones are drawn like this. We're going to go for the whole hog, and vice versa. We have them doing this on the south pole as well. Okay, that would get you 3 out of 3. Okay, you had to have a minimum of 2 field lines drawn, and basically you're just saying, I understand what happens around a magnet. There are field lines around a magnet. If you put something magnetic in those field lines, a force will start. Magnetic force will be applied to the object. So if I put one of these little, so I've got my bar magnet sitting in front of me. If I put one of these staples in near the magnet, I'm going to start creating, I'm going to move that around to my little staple is now sitting on one of the field lines. It's lined up with it almost perfectly. Okay, and if I bring it around the front, it jumps off the page and something heavier, I might be able to line them up. Oh, it does a little bit. There you go. It's lined up with one of the field lines. So I'm holding up the magnet and showing that staple's sticking out at about a 45-degree angle. I got a bit lucky that it's sitting in the right place, but it's sitting on a field line. So if I move it into the middle, there you go, sitting on that field line now. You see that from all the way at the back? And you can do that with iron filings. I could pour iron filings all around this. It just makes an almighty mess. But if that's probably the experiment you've seen at home before or seen in primary school. That is how to draw a barrel magnet and label it. Any questions before we move on? No? Okay. Right. This is a terrible diagram. I think next. Here we go. So draw the field lines around a magnet using a bar magnet. Around a bar magnet using a compass. So you don't need to draw this one necessarily. You could even add it to your previous diagram. So here is our bar magnet. And I say, prove to me that there are field lines around it. Well, we could see them with a staple, we could see them with iron filings. So iron filings would be a perfectly sensible answer here. But if we take our compass, so let's put our compass here for a second. Now, our compass normally does what? Take the magnet out of the equation for a second. What would our compass point towards? North, okay. So, where's north at the moment as far as this compass is concerned? This magnet's taking over, isn't it? The Earth's magnetic field is weaker than this magnet. Okay, so if I draw a field line, and we've already got one of these drawn in our previous diagram, I'm just going to draw it through the compass. Okay. Which way is the compass going to point? Left or right is the answer here. Which way are we going to go for? Left, because that's the north of. Yeah, okay. So our compass is. I'm just going to do a compass with an arrow in it. I know that's not entirely what compasses look like. What if I then moved this over here? Which way would it point then? Anyone want to shout out which way they think it would point? Come on, girls, you're being a bit quiet at the back there. Which way is this one going to point now? The one on the right there. So we've done A. Which way is B going to point? Same way? Anyone want to throw something in there? Who thinks it's going to point the same way? Anyone want to offer up something different? No? Go on.
So it's like point back, like just follow the line.
Follow the line. Which way is the line going?
Like diagonally up, like left.
Well, it's going up, isn't it, really? Okay, so the actual arrow in the compass is going to just line up with those field lines. So at this point here in B, it's actually going through like this. So could you add two compasses to your previous diagram or draw a new one quickly? I don't mind. But we need to know that this is what the compass will do, because you might be asked to draw something similar to this. Okay, so this is one of the demos of practicals that we often do. It's not an essential one, but it really does explain what's going on with magnetism. Okay, it's not touching it, it's just the field line is going through it, because right now the Earth's magnetic field lines are going straight through you. Okay, and if you were magnetic, you'd be lining up with them. Has anyone ever put a needle on a leaf in a bucket of water? Anyone ever done it?
Yeah.
Yeah, you done it?
You put it like it's like a compass, like a compass.
Yeah, it is in fact an old version of a compass. So if you had a piece of steel, or a piece of iron, and you adhere it, so it's called, in layman's terms, rubbing it. Okay, all the electrons, the free electrons inside the piece of steel line up. It becomes temporarily magnetic, which means it's affected by the Earth's magnetic field. You then put it on a leaf in water, and it will turn and line up with the Earth's magnetic field. You've basically made a compass. What's the catch? Which way does the needle point? North or south? You won't know. You'll have to be able to work that one out for yourself, which way the sun is. Okay, so you'll get something that points in the direction of these field lines, but the needle doesn't have an arrow on it, so you don't know which way it's pointing, north or south, but it will give you that line. Okay? Right, let's move it on. Oh, look at that. Pretty diagram appearing on. Right. Induced magnetism demo. This is where I've got to work very hard to try and describe to everyone at home what's going on. So at home, and for those of you in the classroom, I've got a bar magnet here, and I'm going to pick up my staple. We're alright with that? That doesn't seem like magic? Alright. So I've got my staple here now, I've taken it off the bar magnet, and I'm going to take it over to this other pile. Oh, hang on. I'm waving my staple, and it's not picking up any of the others. Was anyone expecting it to? No, because that's not magnetic, is it? Okay. So, let me ask you a different question. So I'll stick that on that one. So I've put my staple back on the bar magnet now. And I'm going to separate these out a little bit so this doesn't go too skew. Right, so the first staple is now doing what to the second staple? It's now connected. So I've now got a chain coming out of staples coming out of my magnet. So I get the third one. Oh, doesn't want to play ball. So the third one. Oh, there you go. And if I spread them out a little bit, what I'm going to end up with is a chain of staples. Now, the staples are steel, so they are ferrite, they're magnetic. But on their own, they're not magnets. Okay, they're just attracted to magnetic fields. I can make my way over, hopefully, and pick up. No, I think I've maxed out here. There we go. I've managed to get a chain of 5 staples, but none of these staples are magnets in their own right. So this is what the word induced means. I've made these staples, why they're connected, the first one's connected to the magnet, I've made them magnetic. I've induced magnetism. Okay, so that's what the word induced means. To prove a point, if I take the first one off the magnet, what's going to happen? They're all going to fall off. See, you already knew all this. Did they? They haven't yet. For a very short period of time, these steel pieces are going to have all the free electrons lined up on them. Okay, they're going to be magnetic. If I wait long enough, which I'm not going to do, there you go. Perfect timing. They all just fell apart. Okay, so for a very short period of time, they stayed magnetic. If I took the magnet away, they lost their induced magnetism, and they ceased to be magnetic. Okay, so that's what induced magnetism means. So the paperclip isn't magnetic. What about now? Okay, so could you use some keywords and write in your own sentence what you just saw? So for those of you at home, the keywords are magnetized, magnetic field, permanent magnet, induced. So I was holding a bar magnet. That's a permanent magnet. So I'm going to give you a bit of a lead here what to write. So we took a permanent magnet. Okay, we applied it to a magnetic force to one of the staples, and it induced magnetism in that staple, which meant that it became magnetic as well, which meant it could pick up another staple. That induced magnetism in that staple, which meant it could pick up another staple. So the magnetism was induced the whole way down the chain. We only got to 5 staples before it became too weak to pick up any more. But as soon as it took away the magnet, it stopped inducing magnetism after a period of time, and the staples all went back to just being pieces of steel. Could you summarize that? Have a crack at it, because if you put all that in one couple sentences, I should say, you've pretty much got a handle on what's going on. So at home, guys, could you on your revision sheets just add in a little explanation of induced magnetism? You've heard me repeat it a couple of times. Go back over, wind it back a little bit, play it out, just turn it into your own words. And this becomes very, very important when we talk about electromagnetism. So we're creating magnetism by electric forces. So we start electric flows, current, which might start giving you the idea that many things around you are magnetic. Some of them are permanent, like a permanent magnet. Some of them are induced, like what we just did there. How far did you get?
I was thinking.
Don't think too long. We'll move on. What have you got so far? Tell me.
I was like, I take a permanent magnet and then just used it on
Used it on an unmagnetic metal.
Yeah, and which induced magnetism. Yeah. So that's what you want to write. And then that induced magnetism was able to pick up another staple which induced magnetism in that. Okay. Okay, so I'm going to move it on there, guys. If you want to come back to that later, you can watch the video back and top it up. Just make sure you've got a fairly solid explanation there. Right, permanent magnets. This is a permanent magnet. I'm holding the bar magnet up here. Okay, a permanent magnet, apart from the fact dropping it's actually quite bad for it, which I just did, never mind that, is a piece of steel. It starts its life nothing more than a piece of steel, and they put it in an oven. Literally, they'll do thousands of these at a time, or when they make really, really big ones, one at a time. They'll put this in an oven, they'll make it really, really hot. Okay, now the reason they make it really, really hot is they want to free up as many electrons as possible. So you make something hot, the electrons inside start racing around faster and faster and faster. That's layman's terms, it's not quite as simple as that, but you get the idea. At that stage, they bring in another magnet, a very, very powerful magnet, temporarily put it near all these really hot pieces of steel, and it induces magnetism in all of those. Then they take that magnet away and they slowly let all the pieces of steel cool down. Now, because they were induced while they're really hot, all those electrons remain in alignment, and our piece of material, our piece of steel, remains magnetic. And a bar magnet like this might stay properly magnetic for about 30-35 years. There is a catch. You start throwing it and dropping them a lot, eventually they'll either crack, which happens quite often, or they'll stop being magnetic. Okay, you can force, because if you're applying energy into it by dropping it, that will, the kinetic energy transfers into thermal energy inside. Thermal energy releases the electrons to move around. They'll go back to where they're not forced to be locked, and it will try and return to its original state. But that's how they make bar magnets. Nothing more complicated than that. Heat them up, apply a big magnet, cool them down. Make sense? So we've got permanent magnets and we've got induced magnets now. That's the whole magnetic world, induced and permanent. So what have I written in here? Steel, okay. The reason we use steel is because you saw here, it's when I induce it, it doesn't say make the staples, they don't stay magnetic very long. But if you do this process, heating them up and inducing the magnetism, they'll stay magnetic for ages. Iron is really easy to induce. If these were iron, these would still be magnetic now. Okay. However, they would lose it in the next few hours. Okay. Other materials, you've got cobalt and nickel, which are fairly uncommon, but they sometimes use them in high pressure environments. Okay, yeah, that's the 3 key points there. I won't get you to write any of that down. We'll just scoot through them, have a quick read, pause it if you need to. If there's any key points in there that you weren't sure about, that we haven't talked about, I think we've covered them all there. Okay. Oh, right, okay. So this was meant to be a 6-mark question. Describe the difference between a permanent and an induced magnet. And for some reason, it's come the other way around. So you should be able to tell me the difference between a permanent and induced magnet. So on your revision material, put 2 columns. Permanent, induced, key points in both. Okay, you do that later on. Right, the Humble compass. Okay, so it's a small bar magnet. The red needle is the north of the bar magnet. The red needle is the north of the bar magnet. That's quite important for this next bit. So the north is attracted to the top of the Earth. So the north is attracted to what normally? So if I got the south, so what are we going to find at the top of? That's north that we put on maps, but that changes, flip-flops all the time, doesn't it? I told you at the start, north and south flip-flop around. Okay, so our magnets and our compass, the north bar magnet is actually pointing to the south. So if you were going to draw the Earth as a bar magnet, it would actually look like that. In fact, I used this exercise with my A-level physics students their first week. I asked them to draw the Earth and I said put a bar magnet in it. Then I asked them to draw a compass and tell me how it's attracted to field lines, and they all do exactly the same thing. They draw a north at the top and a south at the bottom. They draw their little compass and they all go at the same time that doesn't work. The north can't be attracted to the north has to be attracted to the south. Now it's all, there isn't a bar magnet in the middle of the Earth. Okay, let's just get that clarified. Okay, no one snuck in the bottom and chucked one in there. It's actually a big ball of molten iron, and it's molten, it's liquid, and it spins. And because it's spinning, it creates a magnetic field.
Where's that?
In the center,
Oh, yeah.
right in the center. Most of our Earth is made up of iron. It's a huge part of the Earth's core and crust. Hello, good morning.
Sorry to disturb you, sir.
Sorry.
Guys, can you please get all your assessments out and just leave them on the desk, and I'm going to come round and pick them all up. Who hasn't done this?
I just went and wrote
Is there any chance we could do this at the end, just so I'm just recording this, so I can, if that's all right? No, that's all right.
Okay.
For the benefit of everyone at home, you need to have your assessments out by the end of the lesson.
I'll be back.
We'll sort it out at the end, okay?
2 minutes, thank you.
Right, so guys, just pause on your assessments for 2 seconds. I'm sure we'll get time at the end. So this is not GCSE knowledge. Okay, I just want to clarify. I just want to put in context of why people get themselves in such confused when it comes to magnetism. Because if you start thinking of the Earth as one thing, then it doesn't make sense for a compass. But this is not about a compass in the Earth. This is about two norths repelling and a north and a south attracting. If you can get that in your head, you're sorted for 90% of this. Everyone all right with that? Okay, this is just to throw in something in the mix for you. Okay, so what else do we need to know about the Earth's magnetic field? Okay, we just spoke about this. Large spinning molten iron protects us from what? Why is this useful? Other than the fact we now have a compass. Compasses are useful, don't get me wrong, but what else does it do? Anyone else know what the magnetic field does? Did anyone go on the geography trip before? No? No one went on the... You did? You saw something on the first or second night? Because I know Mr. Smith put photos of it up. Northern Lights. Anyone know do you know what the Northern Lights are? Or you just went, oh, that's pretty?
Yeah.
You're allowed to say that was the case. Oh, it's pretty. Yes, it is. It's actually the Earth's magnetic field protecting us from solar winds. So the sun emits huge amounts of energy, and some of them are ions. And they come along, and if there was nothing protecting the Earth, they would just crash straight into the ground, into us. It strips oxygen from the atmosphere. But the one thing the magnetic field does is, because the magnetic field is around the Earth, it creates like think of it like a rock in a stream. It gives the ions a path around the Earth. It forces them. There's just enough of a repel to push them around. So rather than hitting Earth, which would damage us, damage equipment, but occasionally these solar winds get really, really strong. So in 1987, we had solar winds for about a week that took everything offline. We had power grids failing, we had electronic equipment being damaged. Imagine if that was now. What's changed between now and 1987? What have we all got in our pockets? Mobile phones. It wouldn't work. Okay, so we're actually sending probes to the sun right now to measure these solar winds. But if we come back into our context, this is kind of what it looks like. This is a little bit over dramatic, but it gives you the idea. You see the field lines there from the magnetic field in blue, and we're talking about these solar winds that apparently are flame-throwing nemesis from the sun. They don't look anything like that. You can't see ions. You can detect them, but you wouldn't see them until what? They crash into our magnetic field, and we see it as the Northern Lights. Proper name? Aurora Borealis. Okay. Latin name. Northern Lights. Okay. There's a reason why we switched to Northern Lights. Most people can't remember Aurora Borealis. It is literally, and it happened for years and years and years, thousands of years. Humans have walked the Earth and seen the Northern Lights. What would you be thinking if you knew nothing about magnetic fields? Okay, it was all very unknown to what was causing it. You would think the gods are annoyed or something to that effect. But obviously in 1987 they had a real shock. They didn't realise how strong these solar winds could be. They only just started to work out what was really going on. So the two probes at the moment going through the sun's atmosphere. The sun does have an atmosphere as well, it's not air. And they're spinning through it and trying to work out if there's a pattern to these occurring. Pole reversal. This is a bit more fun, this one. I like to pick on pigeons at this stage. So just some key facts, don't need to write these down. And the reason I pick on pigeons here, guys, why am I picking on pigeons? Anyone know why I'm picking on pigeons? They're pointless? No, they are, but that's not the main reason. Go on.
I know that they travel in the direction of something.
Direction of something. Anyone heard of a homing pigeon? You take a pigeon 300, 400 miles from its home and it can fly straight back there? It's true, it's not made up. People race pigeons. They're called pigeon fanciers. I know, it's a terrible name. So these pigeons can find their way back home. Do they have sat-nav? No. Do they have maps and compasses? Well, part of that's not true. They don't have a map, but they certainly have a compass. In the beak of a pigeon is, right down the middle of their beak, they're able to detect magnetic field lines. So they can feel the Earth's magnetic field. In fact, I've seen an experiment which I'm not entirely approve of, where they've put pigeons in a room that they can adjust the magnetic field of. And the pigeons will fly around the room depending on which way they line up the magnetic field. So they're very attuned to where it is. I think that's a little bit cruel, if I'm honest. Well, how else would a pigeon know how to get itself home?
How did we find out that a pigeon can do that?
By working out, watching the way they were flying. They're basically flying along the Earth's magnetic field lines to find their way home. It's quite something that they can do that. So what happens if a pigeon's flying along and the Earth's magnetic field flicks over? They're going to fly in completely the wrong direction. That's a lot of very lost pigeons. I have no idea how pigeons have managed to survive this long. So you can see there's been quite a few reversals. What does this suggest the next one's due? Anyone? So the last one was 780,000 years ago. How often are they occurring, roughly, if we look at the top one? How often is that occurring? So if I put this as a test question, approximately how often do reversals occur? Sorry, I missed that. Yeah, so how often do you think they're occurring? So we had 200 in 178 million years. What's that roughly? One every... Speak up.
700,000 years, probably.
Yeah, it's probably... we'll make it really simple. How about if we said one every million years? Would that be fair? Roughly? It's not quite that. It's slightly more than... It's slightly more off than that. So it would be closer to what you were suggesting. But if we just said one every million years, and the last one was 780,000 years, when's the next one due? Could be any time now. Okay, and there are ways we can prove this, and I think the next slide goes into some of that. Yeah, it is. So this is Magnaflow. So on the Earth's, these are normally oceanic faults, where magma is coming up from the core and going up through fissures in the ocean floor and spreading out. So if the plates are opening up, so the plates are spreading apart, magma comes up and fills the gap. Make sense? It cools into rock. Remember how I said the Earth has a lot of iron in it? Okay, so as that comes up, it's liquid and it's hot. Remember how we make these magnets? We heat them up, line them up with the magnetic field, which is the Earth's magnetic field in this case. So as this comes up, we end up with lots and lots of poles. So these are going to be north orientated, and when the magnetic field is the other way around, will be south orientated. So these are all in pairs, and as they separate apart, right, so they can actually go along and detect this. That's how they can tell how fast these plates are moving apart, where they were, by measuring them against other points when they know that the magnetic field was flip-flopping around. So straight away they can tell how old things are and how often it's occurring, and if they're speeding up or slowing down. So if these ones over here are a really long way apart, and over here they're quite close, you would surmise that it's slowing down, which is a good thing or a bad thing depending on which way you go. And that's part of the application of this. So if you ever see a diagram with north, north, south, south, think of pairs. Think of why have I got pairs? Two things coming north. Oh, they must have occurred at the same time. Everyone all right with that? Okay. Pretty much gets us to the end. So I'm going to stop the video because I've got to ask these guys some questions. So make sure you summarize everything and we'll go from there.